we're going to talk about springs. Not much has changed. We're just going to combine springs. So as a reminder, springs are governed by Hooke's law. Hooke's law says that the force due to a spring is K times delta X. Now, specifically, there is a negative sign out in front of that because if I have a spring, I always do that. If I have a spring, let's say this is its equilibrium length, and I stretch it past that. So now it's out here, it's been stretched an extra delta X, right? Which direction would the force on this spring be? Would it be to the left, back to equilibrium, or to the right, further away? To the left, right? So even though delta X is positive, right, my force needs to be negative newtons back towards equilibrium. Same thing goes if I have a spring, and this is its equilibrium length, but it's been shortened some delta X. From its equilibrium, this delta X would now be negative, but the force needs to be positive because it's going to point back out towards equilibrium. So that's the reason why there's a negative sign in Hooke's law. It's because spring force is a restorative force, so it wants to go back to equilibrium, so it's always going to be working opposite whatever the stretch or compression is. Okay? So that's Hooke's law. It makes perfect sense, but what if I want to have two springs acting on my object? So what if I want to have springs in series? That means I have one spring, and then I attach another spring and hang a mass off of both springs. Now, the first thing you could do is say, okay, well, I would just add together the forces. There are two of them. But we don't want to deal with multiple springs. So what we do instead is we said, we're going to treat this like one spring. We're going to treat this like one spring with a force of negative K equivalent times delta X. That K equivalent represents the spring constant if this was one spring. That's its job. It just represents what is the spring constant if it was just the one spring. If you took honors, or if you've already taken Physics 2, or if you've ever seen anything about a circuit, you might remember the word series. In circuits, that means all my components are in line with each other. And we calculated the equivalent resistance for all of those components, light bulbs, resistors, all that kind of stuff. These work very similar, okay? Except for they're actually capacitors in that K equivalent in series is actually the sum of the, those are ones, 1, 2, sum of the K constants, the inverse of that. What? So the K equivalent for a set of series springs looks like the resistance in parallel. So it's the sum of the inverse of all of the K constants, so 1 over K. You add all those up, and then you take the inverse of it, 1 over that.
Why don't you just keep them all the same?
Because that would be something different in parallel. So I'll demonstrate with these things, right? This is a 200-gram mass. So in newtons, that's 0.2 times 10. That would be roughly 2 newtons. So on my spring here, it comes down to 2 newtons because I'm measuring it with one spring. Now, if I add a spring, this isn't going to work perfectly because these springs have mass. So I'm going to demonstrate. But what happens is the stretch on both springs actually increases. The reason for that is because the equivalent K constant for both of these springs added together is less than the spring constant when they were 1. Okay? By doing this equation, right, the way it works out is that my equivalent K constant will always be less than my largest constant, the constant of my largest spring. And so when K equivalent is less, the stretch of the springs is more. Now, we always measure that stretch of the springs from whatever their total equilibrium is. If this was the total equilibrium for both springs, then I measure delta X as that difference after both springs are combined. So in series, and I can, if you want to come up here and test this in series, I'm showing it to the people on the video so you can also watch the video. In series, instead of measuring 2, this one measures well over 2, and this one still measures 2. If I thought that they were adding together, I would get a smaller distance, and therefore it would measure less. But in series, that's not how it works. That brings me to the other option of how to combine these, which would be parallel. Just like in a circuit, I could also do this in parallel. That would actually look like 2 springs parallel to each other, holding up a mass, like that. In this case, I again want to treat it like one spring. So I'm going to find the K equivalent. What we find is that in this case, the K's just add together. So my K constant's going to increase, so the amount they're going to stretch will decrease. So an individual one of these springs is going to measure 2 newtons. It's measuring 2 newtons right there. I'll show the people at home 2 newtons. When I add 2 of them in series, or I'm sorry, in parallel, almost, it's like catching a fish. I've never done that once in my life, so this should be the same. When I have both of them, I'm going to try and leave them as straight up and down as possible. You can come test this yourself. They're both at 1 Newton. So that displacement halved because I added the K constants together, so the K constant doubled. So you might think in series they would add together. That's incorrect. In series, it's the inverse sum. And in parallel, that's when I get them added together. Question?